So much. I think you actually see quite a bit of a relationship. The notes are coming in a minute, but most of today is trying to change the wheels a little bit here. Professor Eager talked a lot about steel and how much we use steel for the main benefit that it turns out to be really cheap as a process. It's not as cheap as concrete, for example, but among the metals, it's one of the least expensive to use. So to the extent that it fits your purpose, that you can afford the weight, and that you can deal with the fact that it will corrode in a lot of environments, you should use steel. So related to that, I decided to start this 6-hour module on mechanical behavior and environmental behavior, talking about corrosion of steel. And the way I want to organize the 6 hours, this is still preliminary, but so today is corrosion of steel, and I want to switch gear a little bit after that. I think talking about corrosion of stainless steel is a logical sequence. So next class should be tomorrow. We're still a little bit, yeah, perfect, thank you. We're still a little loose on who is going to be teaching tomorrow, but you'll have a lecture, a live lecture. Remember always here, as far as this introduction, is stain less. It's not stain free. It's a very minor distinction, but if you talk to a lot of manufacturing people, they'll think of stainless as this greatest thing invented, while in fact we have a lot of failures of stainless steel, both in terms of corrosion, so loss in section, but also in terms of stress cracking. And that's what we're going to address next class or the following. We'll see exactly how it goes. So I want to talk about the corrosion, and then I'll spend some time doing mechanical of metal, but it's going to be very short. There are online modules for this class that you can look at. I did life assessment back maybe 2 or 3 semesters ago, essentially dealing a lot with mechanical behavior and fatigue and creep and all those things. So we're not going to go there this semester. I'll introduce some concept, but I'm mostly going to tie it back to what we've seen in terms of corrosion and talk about embrittlement. That's another problem with steel at cold temperature, and why it's happening, because we went through that deformation processing together, so I know you have some concept of what makes the deformation take place in the material. And the embrittlement is essentially caused by preventing the deformation to happen. If you prevent it, you reach a stress level where you can break the bonds between the atoms. So that's the bottom line idea. I think it should be relatively easy for you to grab that concept. And then for the next 3 hours, we're going to switch to talk about plastics. It's not something that was traditionally in the class, but I know that a lot of people do research related to polymer, living tissues, and all sorts of stuff. So I'm going to give you some overview on plastics, then talk about the mechanical behavior and also the environmental resistance. Try to make it essentially that 6 hours as worthwhile for you to think about what happens to the structural material when you put it in a certain environment and a certain mechanical characteristic, excitation, whatever is actually happening, if it's an impact, a long-term load, a short-term load. We're not specifically trying to design here. I'm really going to focus on the mechanisms of what is happening in terms of design. Again, it would be the life assessment module, or even the material selection class I gave last term in the spring of this year. Was a little bit more specific on what to do in which situation. You'll get that also as part of what's left of Professor Eager's live lecture in terms of what you decide to use for which application. You always start with the least expensive. If you can make it out of concrete, it's great. Well, dirt is probably the best, the first option. Then you go to concrete, and eventually you become into more and more expensive materials. So I want to talk about this specific project because it was one of those, and it ties between material selection and mechanical behavior and corrosion. This is a project I worked on as a spin-off company building these wind turbines that have a shroud. So you have here all the blades and essentially the gear system with the generator. The difference is that you funnel the air around it. So the airflow is from the smaller side to the lower side. What happens, it creates a suction on the back end. I may have included this image. So you have a suction taking place here, and it's accelerating the flow of the air through the turbine. It allows you to build a smaller wind turbine and provide the same power. It's a great idea, but it's like everything else, now comes cost. How are we going to do this? Because it's easy enough to have the pole here and attach the generator to it and have the blades. It's very cheap. The way they set these up, they're still government subsidized, but it's just a straight beam of steel going up. So apparently, if you're trying to determine, okay, this year I want to build so many wind turbines, you have to get the price for those beams because it's an important cost in your installation. The other cost is the foundation and the generator up there, but they try to make this as affordable as possible because you don't generate a whole lot of electrical power. It's not a constant source. So in terms of really making this a good investment, you need a low entrance cost, a low capital cost. So the idea of adding this shroud system on the outside, you're looking at well, I don't know that the caribou or here's a good representation, but the diameter I was working with was around 70 feet. So you need to form this shroud with a diameter of 70 feet that will withstand, you know, depending where you are, definitely high winds. You could have ice forming on it. And it has to last through the years. So they gave us initially a budget. It was outrageous. I think they said $50,000 for the production of each shroud. And I said, no, you're crazy. It's not going to happen. And they were like, okay, well, what is your best bet? I said, you know, if you double it for 100,000, we may be able, you know, on a production run to get there. And they were like, well, you know, we'd like to be optimistic, but we'll take that as a number. So even $100,000 for production, it's just so big. And the connections are critical. If it starts falling apart, I mean, you don't know. The one that I worked on is installed here by the Logan Airport. And there'll be people, maintenance people around it. I mean, they may decide not to go if it's a big windstorm, but it's just a big system. And there were some, actually after the erection, there were issues about it, not related to the work of my firm that I work for, but some other people doing the gear systems, just because, you know, cost again. They were trying to optimize it, but there's some wind off because you assume that you're going to be aligned with the wind. If you're not, then you're adding load to your gear system. So the idea here is just to tell you this happens all the time on a big structure where you'd like to make it cheap, but then you say, okay, fine, we'll make it out of steel. And then all of a sudden, everybody, you know, in the marketing team and all that gets all worried that it's going to look rusty and people would think it's a piece of crap. So that's what we were faced with. If you want the cheapest, we'll make it out of steel. Yeah, it'll stay, but there's no salt. I mean, it's up there in by the ocean, so there'll be some salt. So you have to clean it, you have to put a good coating, and you probably have to do a rehab after 10 years. but it will be the cheapest way. Now, for a company that is in spin-off mode, get all the government subsidies, and it probably is going to be there in 5 years, it's not a good idea to erect a prototype that by the time you become commercial, it's starting to stain. So they just didn't want to go there, and we had to essentially come up with an aluminum design and also a composite design. The composite was by far the most expensive way to do this, but they they liked the idea of composite, and they were still at the research stage. And there's nothing wrong with it. You know, when you really start a new product, it's good to be open-minded. But at the same time, once you narrow it down, you have to also consider the common alternative, which a lot of times is steel or aluminum or very common material. We looked for this also in using fabrics. The problem with fabrics is you still have to hold it there, so you still need a superstructure behind it to have it hold in place. One advantage was in high wind in hurricane situation, you could design it that everything just tears apart and you don't have a collapse of your structure. So that was one advantage. But in terms of again, cost and putting it together, how many supports were required to have essentially, they had this very nice idea about the surface tolerance on these double curvature surfaces, but it's a little bit like building an airframe, except that you don't want to pay any money for it. So it was very, very, very challenging in terms of a process. What would have been the best alternative to aluminum was steel, but galvanized. It doesn't have the great white appearance on the first place. If you're going to paint the galvanizing, that's possible, but now you keep adding more cost and you keep adding more cost. You need a lot of surface preparation over galvanizing, and we'll talk about that a little bit. But essentially, just straight hot dip galvanized, I think would have just done the job perfectly fine. There will be some staining in some of the connections where you had scratches and all of that, and that was still something that they were not really happy to get into, and they didn't really like the dull gray color. So that's where the engineering stopped. I told them, you know what, just go and do whatever you want. I mean, these are the options. The cheapest is steel. After that, you got galvanized steel, and then yeah, we can do aluminum. If you want to do composite here, fine. We'll happy to work and develop it, but you're not going to make it. That's not what you're going to use for fabrication. Any question on that example? All right, I made it a little comprehensive. So we're talking about steel, and this is a piece that came out, this tow drive tunnel. I was looking for it, but I couldn't find it this morning. It's about 3/4 inch thick, but it is not the thickness of the material you lost, thankfully, because this came out of a 1 inch beam. What happens with corrosion of steel, it just exfoliates, it just grows. The oxide has a much lower density, and it's not a compact and a perfect crystal. It's just got a lot of oxide and loose pieces in it. So you grow by a factor of 4 to 5. So if it was 3/4 inch, we only lost maybe between a 16th and an 1/8 of an inch here of the beam. It was at an expansion joint, so there was essentially water from the road coming from up above down there. It was very difficult type of situation to be in for an engineer, because you see the degradation. You've been told, oh, we're utilizing like 95% of the allowable load on this beam, or we're overstressed. Okay. And then nobody wants to, there's no mayor that will say, okay, we'll shut down stow drive for 6 months. I mean, they're just doing it for Longfellow Bridge right now, but nobody is really happy with this. It needs to be done, but you try to delay it as much as possible. I was under Longfellow Bridge 3 years ago. They were doing work essentially around the support for the train, the red line train. What happened is the same story with water. Poor drainage, you get chlorides in the connection, it just starts to corrode very quickly, and you have to change it. So they were doing partial repairs overnight, just doing a few beams at the time. They had the horizontal beams. There was the beams for the decks, but also the vertical posts connecting the arc. Thankfully, the big arc still had its thickness. That's 100 years old, and it's all riveted. And we'll get to that in a minute when we talk about what happens. So corrosion, I don't remember the percentage of our gross domestic product, but it's not negligible. Essentially, when you think about what causes things to require replacement, you have corrosion, you have wear. These days with plastic, you just have the UV degradation. You can have creep. Sometimes it's just out of fashion, like automotive. But in general, there are a lot of problems with corrosion in industrial setups. If you have tanks that are underground, above ground, piping, you really have to worry about is the environment going to be compatible to get my 15, 20-year life, or maybe you want a 50-year life. It depends what you're looking for in terms of what piping you're really going to put together. So here you have a sort of a distribution of what happens more often. So the general corrosion, which is what I showed you with that little beam piece, is the most common. But you see right underneath, stress corrosion cracking, that's a completely different mechanism. And it still happens a lot, almost as often as general corrosion. And I would say one of the reasons is everybody knows about general corrosion, and you see it very quickly. If you put something together, it starts to corrode, and you can monitor the thickness loss. Stress corrosion cracking is more subtle. The piece of aluminum on an airframe will look fine, and you need to come with non-destructive testing method to find out, oh, I have cracks. So it's a lot more subtle, and it's a lot more difficult to observe than just the general corrosion. Pitting is very common. Copper pipes tend to pit. If you have small leaks in copper pipe, normally it's not the whole thickness that you've lost, it's just a small area. And then you have all these other mechanisms that are unfortunate, and I'll try to cover some of it, but in the interest of time, we're going to try to focus here on general corrosion, galvanic corrosion, and what happens a lot, what you should know for sure. And then it's important to know hydrogen's just, it's not good in general. If you're going to have chloride and hydrogen with stainless steel, aluminum, you just have to be very careful. You can form cracks very easily. It's the same with plastics. If you have oil or oil contaminants with plastic, they tend to initiate cracks. And we'll cover that in more details. So the modes of corrosion. Uniform, that's the beam we talked about. Galvanic is this term, I'm sure you've heard it, if you're course 3, even if any course you've been in. Just think of like simple layout in a pump. Lots of time you're going to have some stainless steel components. You may have some cast iron. You may have some bronze for impellers. You put it all together, and if the pump is not running, you're at risk for a disaster, because you're putting together, connected together, different components that are in water. So you can have that connection through the water and through the metal with the similar metal, and you can essentially have a lot more corrosion than you'll expect. Now you may be able to afford it if you say, okay, it's okay if my structural steel, my cast iron corrodes a little bit. All I want is make sure that between the impeller and the guide that's going to remain stain free, or that it's not going to have a buildup. But it's part of the process here of trying to optimize and make sure that you don't have a problem. Ideally, we will build pumps out of all the same material. In practice, have yet to see it. It's very unfortunate because a lot of times some of the issues coming up with pumps would be a non-issue had they spent a little bit more money, you know, on this component or this component. But it's an industry that goes by a certain standard. So if it's a pump that's going to be running all the time, no problem, because you don't have the time for the electrolyte to really get the reaction going between the two metals if you have flow through it. But when it's stagnant, if it's a backup pump, that's where I've seen more trouble with this type of corrosion. Crevice corrosion is that Longfellow bridge. That's the main thing we were worried about, because under the rivets, if you have two splices of steel and you rivet them together, you have that little corner where there's not as much oxygen from the air circulating. You can still have the chlorides coming from the top and essentially have a very high overall corrosion potential. But instead of having the corrosion everywhere, you localize it. The differential in the oxygen potential gives you more of a driving force. So that's unfortunate. It happens under gaskets as well. So in general, and that's one of the reasons in industrial plants, they will tend to fully weld some of the vessels to avoid having these little corners that can cause the local corrosion. Now, if you have a welding defect, that is where the corrosion is going to start, and I've seen that quite a bit. Yes?
I noticed also on the Longfellow that they had corrosion on the rebar and popped out the concrete that was over the top.
Yes. So the issue with concrete and rebar is very interesting. And we will actually get to understand why we try to put the steel in the concrete. It prevents, it stabilizes the steel by increasing the pH. The pH of concrete is higher. So what happens is, not all the time. Normally you'll have some degradation of the concrete, changing the local pH, and then you'll have the corrosion of the steel. Not all the time, but a lot of times the degradation actually starts on the concrete side. Obviously, you have some differential in terms of elasticity and expansion that will also make that interface prone to starting the corrosion. But as long as your piece of steel is embedded in the concrete and the concrete is sound, you're good. You can, even if the oxygen gets to it, it's not going to react because you have a higher pH. So you pacify. And we'll get to that. It's a good question. Any other question? I mean, I'm going through this. I'm trying to give you examples. I'll tell you one thing. I hated corrosion when I was a student. I totally did. I went for exchange study program. I ditched out the corrosion classes, and I took some other classes abroad, and I was happy about it. And then it got to me down the road that I really had to know how it worked. And it's not so much about anode, cathode, and trying, oh, is it the plus or the minus? It doesn't matter. It's a battery. There's always going to, there's a more noble material, there's a less noble material. Eventually, if they're not physically in contact, if you don't run a wire through them, they're okay to sit in the same bat. But as long as they're connected as part of the same assembly, if they're sitting in the bat, they are at risk. That's what you need to remember. And then, yeah, if you love the, the terminology, you can get in very fancy about it. And you can start to wonder why, if this is all about anode and cathode, why does it happen even if you have just one piece, right? I wonder about that, and that's why I have the little video, because it's so simple in the end. All of these mechanisms they all involve these reactions of positive and negative. You need a cell. You always need a cell. What happens is if instead of being over a large surface, it's localized over a small area, then you get a lot more corrosion. But overall, it's the same process. The intergranular, it happens in the grain boundaries. You have segregation, you just have a different potential there, and that's why it's localizing there as opposed to going through the core of the grain. So it's all about establishing these differential. A dead battery doesn't give you anything, but if you have a potential between two phases and you connect them, you need the electrolyte, so the ion, to be able to communicate, and the electrons on the metal, inside the metal. That's all it takes. Just different types of cracking that can happen. So I pretty much covered that. One thing that's important to know here is it's not always the exact same reactions. You know, in this case, you're going to produce hydrogen gas, it says. Well, it may or may not. It depends on pH, the differences in potential between the electrolyte you're in. And that's why when we talked about hydrogen embrittlement of steel, what you try to avoid is forming the hydrogen on the steel. And that's by, you can tell whether it's going to be a problem or not by looking at all the environmental components. But it's always an oxidation and a reduction. It's just not always the same oxidation and the same reduction. So that's important to keep in mind. So here in an acid, of course, things go really badly, and you're forming hydrogen ion. So you're not forming what molecular hydrogen in this very acidic situation. All right, let's do the video. Just 1 minute.
Even hard, tough metals can crack as a result of corrosion.
From the, I don't know, it's your guess when it was made.
Under gaskets or in sockets. Corrosion can also have the effect of removing one of the constituents of an alloy, leaving a weak residue. It is the purpose of this film to explain how corrosion occurs and some of the things that can be done to stop it. The basic cause of corrosion is the instability of metals in their refined forms. Because of this free-energy relationship, the metals tend to revert to their natural states through the processes of corrosion. In the case of iron, the action of rain forms rust. When you analyze rust, you find it is iron oxide.
Yeah, and people will put it under the SCM to figure that out. Sometimes.
In rusting, iron has simply reverted to its original native state.
All right.
The nature of corrosion is almost always the same. A flow of electricity between certain areas of a metal surface through a solution capable of conducting an electric current. This electrochemical action causes destructive alteration or eating away of a metal in areas which are called anodes, where the electric current leaves the metal and enters the solution. We have the presence of an electrolyte as one of the first requirements of corrosion. An electrolyte is any liquid that contains ions. Ions are electrically charged atoms or groups of atoms in solution. Pure water, for example, contains positively charged hydrogen ions.
I gotta let it go a little bit because there's really one thing that I want you to see on the screen because I think you may remember it. This video apparently doesn't have a current version, so I took essentially a corrosion protection class from the National Academy for Corrosion Engineer, and the instructor was like, well, this is the best I've got, and I'm sticking to it because, you know, everything else, you can make it look more fancy, obviously, but it's really the key of what's happening here that you have to keep in mind. And I've been explaining corrosion to 6th graders, to civil engineers, to lawyers, to to just about everybody. Explaining to you guys is the easiest, but I still want to give you kind of the core. The core is, it will always take place. and it's a question of rate. And the best way, because we don't find metals naturally, and that was the beginning of the video here. They always in the form of oxide. It's their stable state. So if you let them go, they go back to that state. Copper does. I mean, gold is an exception. There are a few exceptions, but in general, that's what happens. The main thing, I hope it gets there soon. I mean, I watched this probably 5 to 10 times. Yes?
So I know, like, you can do the sacrificial anode to save your...
Yes.
Right?
Yes.
Is there a way to actually do that on mass, like, large scale for bridges, or is it just not possible?
Okay, it's a very good question. Let's address it after this part.
From the solid surface and entered into solution, while the corresponding negative charges in the form of electrons are left behind in the metal. The detached positive ions bear one or more positive charges. Each iron ion carries two charges and releases the electrons which travel through the metal to the cathode. What has been taking place at the cathode all this time? As you can see, the electrons reaching the surface of the cathode through the metal have been meeting and neutralizing some positively charged hydrogen ions, which have arrived at the center surface through the electrolyte. In losing their charge, the positive ions become neutral atoms again, and they combine to form molecules of hydrogen gas. The reduction of hydrogen ions results in the accumulation of a relatively high concentration of hydroxyl ions, which are left behind to increase the alkalinity at the cathode, or to make the solution less acid here. The formation of hydrogen in this type of anode-cathode corrosion cell can be shown by placing a piece of ordinary iron in a solution of hydrochloric acid. A vigorous formation of hydrogen bubbles is seen. Under such conditions, the metal corrodes very quickly. The usual dissolution of the metal is occurring only at the anodes, with hydrogen bubbles forming only at the cathodes, even though it may appear that they are being released all over the surface, rather than at well-defined cathodic areas. The anodic and cathodic areas shift from time to time. This permits naturally uniform corrosion to occur. If we could see this action through a powerful microscope, we would see many tiny anode and cathode areas on the surface of the metal. These areas are often extremely small and so numerous as to be almost inseparable. There are many causes for this, such as inclusions in the metal, lack of homogeneity, surface imperfection.
All right, that's it. If you have uniform corrosion, it's still the same. It's still an anode and a cathode. The only difference is instead of keep having the anode at the same location and digging into the material to form a corrosion pit, it goes back to another location. It's stable. Yes? We use monocrystals mostly for creep resistance at high temperature. Under those conditions, it's typically just air. It's not aqueous corrosion. So at high temperature, we tend to say oxidation and corrosion at ambient temperature. I actually don't know if you completely avoid the oxidation. I doubt it. There's always still going to be dislocations. There's still going to be some potential to have these anodes and cathodes. You're never going to have an atomistic, surface finish, even if you had a single crystal. It's a very good question. Yes?
What about paints like Rust-Oleum?
I'm sorry?
Paints like Rust-Oleum?
Yeah, well, we'll get there. You guys are really interested in that one. Okay, I'll start. I'll start with the idea of let's protect everything. Let's just use zinc or magnesium are very common as a sacrificial material. And let's see, these are all white stuff, or I got colors here. No, no color. Okay, so this is the self-drilling fastener we had yesterday. We inserted it, well, maybe you need to do something different here. Give it a purpose. So we put another piece of material. It goes to both of them. Then we have the head. So this is just a lap joint, turns out. That's all we wanted to do. I'll galvanize this which means it's my sacrificial material. Now, this is a building, say, and hopefully it's not soaked in water. So you'll have dripping water around it, you'll have condensation, but it's not in a pool of electrolyte. What happens then is this zinc here is not going to protect this steel. It's too far. It doesn't have a drip of water that connects the two of them together. And that's one limitation of using the galvanizing and sacrificial anodes for bridges or everything, because of course you have the paths for electrons here through the metal, because you just drill through it, so it's electrically connected. But here, unless all you want to do is protect yourself against flooding, you don't get that benefit here. You will get it in practice up to about 1/4 of an inch. It's approximate, but I had to use that, make those assumptions before, and that's kind of thinking about, you know, 2 droplets next to each other or something like that. That'd be essentially where you have to worry about really getting corrosion to take place. Sometimes you can just have a very high moisture layer. In oxidation, you don't have a liquid, but you still have a little bit of an electrolyte very locally that will, you know, create that anode and cathode effect. Yes?
You never want to use like a more noble material as a facet, right? Or a less noble. So
That,
you had hitting on that screw, then it's just going to pop.
yeah, so that's the best. That's really true. And this typical example for buildings, if you have copper roofs, you can't use any steel nails or screws or whatever. You have you could potentially use stainless steel, but even that is risky. You're creating yourself a condition where it's more difficult to design. The opposite tends to